Good day, I'm Norman Wobbeger. Today I want to introduce a very important function that plays a key role in rational trigonometry in the plane, but also in setting up projective geometry, even in one dimension. It's a very lovely formula, and I hope that you will like it. Okay, so to introduce it, let me remind you that we had a triple quad formula in the one-dimensional situation. We were just talking about points on a line. The affine one-dimensional line with points just given by single numbers. The quadrants between two such affine one points, just the difference between the coordinates squared, making it symmetric and algebraic. So this is some kind of measure of the non-identity of the 2 points. If the 2 points are equal, then this equals 0. And the difference is how you tell whether something is 0 or not. And the fundamental formula in this subject is the triple quad formula, which tells you what the relationship is between the 3 quadrants that you get by looking at 3 affine 1 points. And the relationship is q1 plus q2 plus q3 squared equals 2 times q1 squared plus q2 squared plus q3 squared. An asymmetric form, which is a little bit shorter to write, is that q1 plus q2 minus q3 squared equals 4q1 q2. And we saw this formula sort of appearing in many different manifestations as we went further along in our study of affine geometry and metrical structure. Okay, we're going to find a similar kind of thing happening in the projective setting, but we need a replacement for this formula that's valid in the projective setting. So let's begin by setting the stage and saying what the geometry is that we're considering. So we're going to be looking at one-dimensional Euclidean projective geometry. That means we're looking at the projective line, and we're adding to it a notion of quadrants. We'll call it a projective quadrants to distinguish it from the one-dimensional Euclidean affine quadrants that we've just been talking about. And here's the definition of what that concept is going to be. We have 2 projective 1 points, A1 and A2. They're given in terms of coordinates. A1 is x1 to y1, there's a proportion, and A2 is x2 to y2. And we're visualizing these 2 projective 1 points as lines in the 2-dimensional plane. We don't have to do that, but that's a very nice visual way. So there's the projective 1 point whose name is 3 to 1, and there's the projective 1 point whose coordinates are 1 to 2. Right, so what are we going to do? We want to assign to 2 such lines a number that is some kind of reflection of how far away they are from being equal. So equality is a good place to start, asking ourselves, when are these 2 things equal? Well, they're equal when the proportions are equal. In other words, when x1, y2 minus x2, y1 equals 0. That quantity exactly captures when the 2 things are equal. So a natural thing that you might think of is, why don't we just define the quadrants to be what I just said, and we'll square it so that it's symmetric. That would be exactly the same kind of thing as we did in the affine case. We took the difference and then we squared it to make it symmetric. So why don't we do that? That'd be the most natural thing to do. We don't do that because it's not well defined. Because if you multiply this proportion, say, by 5, multiply x1 and y1 by 5, then the proportion itself doesn't change. But this quantity will change. It'll change by a factor of 5 squared. So we need to adjust for the fact that if we scale x1 and y1, that this thing multiplies by the square of that factor. We need to compensate by having something in the denominator that will essentially cancel any such scaling term. And here's what we're going to do. We're going to take x1 squared plus y1 squared and multiply it by x2 squared plus y2 squared. So both of these are quadratic in the coefficients. So if we multiply x1 and y1 both by 5, then the numerator will multiply by 5 squared. Because of this term, the denominator will also multiply by 5 squared, so the whole thing is unchanged. So you can think about these 2 factors down here as being sort of normalizations that just ensure that this quantity is unchanged under scaling. And you may remember from our discussion in the affine case that this thing here has the form of a determinant, and it's really the area of a parallelogram squared that we're talking about, or the quadria of a parallelogram up to a scalar. So it's really like a normalized quadria of a parallelogram, but we're actually thinking about starting just in the one-dimensional situation here. So for example, if A1 is 3, 1 and A2 is 1, 2, then how do we determine the quadrants between these 2 points? We take 3 times 2 minus 1 times 1, that's 5, and we square it. And we divide by the sum of the squares here, which is 9 plus 1, or 10, and multiply by the sum of the squares here, which is 1 plus 4, 5. So it's 5 squared divided by 10 times 5, which turns out to be a half. That's a rather special projective quadrants. In the plane here, that turns out to be essentially equivalent to having an angle of 45 degrees, or pi by 4 if you want to use that system. This is a completely rational kind of approach to the separation of lines. And we're just applying it now to this one-dimensional setting where we're only talking about lines through the origin in this one-dimensional projective setting. So here's a fundamental definition of the projective quadrants between 2 projective one-points. The definition of the projective quadrants is closely associated to an important identity that goes back 700 or 800 years, to Fibonacci or Leonardo of Pisa. In fact, arguably it's perhaps even traceable to Diophantus, who lived a few hundred years after Christ. Here's the identity. x1, x2 plus y1, y2 squared plus x1, y2 minus x2, y1 squared equals x1 squared plus y1 squared times x2 squared plus y2 squared. So if you haven't seen this identity before, please check it for yourselves by expanding both sides and seeing that they simplify to the same thing. Okay, so this identity allows us to rewrite our formula for the projective quadrants. So here's our original formula, that the quadrants between the projective point x1 to y1 and x2 to y2 is given by this expression. We recognize that as this term divided by the right-hand side. So using this formula, we can rewrite that as 1 minus this term divided by the right-hand side. Because if you divide everything by the right-hand side, then this over that right-hand side plus this over that right-hand side equals 1. And this is a very nice alternate way of thinking about this projective quadrants. In fact, we could have also defined it this way. That connects to what's called the dot product, or standard Euclidean inner product, that's familiar to most students who have taken a linear algebra course. So for example, suppose we have this situation here where we have one line which is 3 to 2, passing through the point 3, 2, and this line here, line 1 to 4, passing through this point 1, 4. Then this thing here would be 1 times 3 plus 4 times 2, that's 11. So there'd be an 11 squared here, and then the sum of the squares here would be 17, and the sum of the squares here would be 13. So another form for the quadrants between these two projected one points would be 1 minus 11 squared over 13 times 17. Now when we write it this way, then the student of linear algebra says, aha, wait a minute, I've seen this expression before. If we take a square root of this expression, take a square root in quotes as usual, then the student would recognize this is the cosine of the angle that's formed between the two lines, say theta. Okay, so this is actually problematic to say exactly what's going on here in this context, because angles are in fact quite delicate things to define correctly, and they require infinite processes. And also these circular or transcendental functions, sine and cosine, also require infinite processes, so they're also dubious. Okay? But if we play along with the standard game, then we see that this is the standard expression 1 minus cos squared of the angle, and so it has to be the same as sine squared of the angle. So this is a good way to sort of ground you if you are based on the standard classical training. You can think about what the projective quadrants is between these two lines as just the square of the sine of the angle between them. In fact, there's more than one angle between them, because there's that angle, but there's also this angle, or there's this angle. There's a whole host of angles there. Fortunately, they all have the same square of their sine. The angles are different, but you take their sines and square them, then it no longer matters which direction you're going. You're always going to get the same number, which is this projective quadrants. The projective quadrants is a purely algebraic thing that you can work out just with a pencil, or maybe in your head, like we did here. There's no infinite series required. There's no calculus notions to define angles. So this is very much more elementary, sort of ultimately more fundamental kind of number to associate to two projective one points, or lines to the origin in our two-dimensional space, if you prefer. Okay, so it's very important to keep both of these ways of thinking about the projective quadrants in mind. So since this is a departure from the way students would normally think, it's important to stress that there is a good reason why we don't use the angle theta to measure the separation of the two projective points A1 and A2. Although, yes, we can think about them as being lines to the origin, and classically there's an angle. In fact, the actual existence of this angle is highly problematic. And you can see that in terms of the standard sort of derivation of the angle from the dot product. All right, so the dot product here divided by the length of V1, the length of V2, that's the standard thing that one does. And then one takes a cos inverse of that in order to find an angle. Okay, so students these days, including students at UNSW, are taught how to go through these motions. And invariably, there's a lot of pressing buttons on calculators, because that's ultimately really all what you can do. To actually make progress in evaluating something like this, you have to go to floating point. You have to give up the dream of all those infinite miles and miles of decimals out there and just concentrate on the first 10 digits or whatever. Okay, it's all you can do. So there are square roots here, and you want to evaluate them, infinite processes. And then there's this rather complicated arc cosine or cos inverse function, which is yet another infinite process, which we'll talk about at some later stage. But the point is that in reality, to actually evaluate these things correctly, that is, completely accurately, is essentially completely futile. It's impossible. Okay, so it doesn't really work from a pure mathematics point of view, even though one can make calculations. But it turns out that one can make much better calculations by trying to get rid of all these transcendental irrational quantities, as you're slowly, I hope, starting to appreciate. All right, so there's close connection to the modern approach, but we're trying to steer away from all that real number nonsense, and that guides us in the right direction, because we know we can't take square roots. We know we can't do infinite processes. So we're not going to go down that road, and we're going to find a better road. This projective quadrants that we've introduced into this projective setting allows us to define a notion of perpendicularity between projective one points. How does that go? Well, if A1 is x1 to y1 and A2 is x2 to y2, we have two projective one points. We say that these 2 points are perpendicular, and we write that perpendicularity like this, precisely when the quadrants between them is equal to 1. Quadrants equals 1 is our notion of perpendicularity of our two projective one points. And from this alternate form of the projective quadrants, we can see that this condition of the quadrants being 1 is exactly the condition that this numerator here be 0. And that does very directly connect with notions of perpendicularity in the plane, in the affine plane with the Euclidean structure. So this is the standard way of defining perpendicularity of two vectors in the plane using linear algebra. So for example, the point 3 to 4 is perpendicular to the point minus 8 to 6. And that's because 3 times minus 8 plus 4 times 6 is 0. 1 to 0 is perpendicular to 0 to 1. Those are our lines through the axes, if you like. And we can also have fractions involved, so 2/3 to 1/5 is perpendicular to -3/10, because if you multiply these two, you get -2, and then you multiply these two, you get +2, and you add them up, you get 0. So perpendicularity has a very nice interpretation, purely in terms of the projective quadrants. We don't really need to know anything about dot products. Okay? It's just we have two proportions, we have this definition of the projective quadrants, and perpendicularity comes from that. So let's make note of a few simple facts about our projective quadrants. It's symmetric. The quadrants between A1 and A2 is the same as the quadrants between A2 and A1. There's a sort of an identity rule that the quadrant is 0 precisely when the points are equal. The original definition had an x1, y2 minus x2, y1 in the numerator, and so the quadrants will be 0 precisely when that numerator is 0, which is exactly the condition that those two ratios or two proportions are the same. Okay, that's the basic condition there. This is the condition of equality of these two proportions. And the third observation is that the projective quadrants is always between 0 and 1. These sort of extreme points of being equal and being perpendicular. And this follows from the two different forms we had of the projective quadrants. So here's 2 points, and here's the original definition, and then here is our alternate definition obtained from the Fibonacci identity. From here we can see that the quantity is always positive because everything here is positive. And from here we can see that it's always going to be less than or equal to 1 because it's 1 minus something which is completely positive. When I say positive, I mean greater than or equal to 0. All right, so both forms tell us that this projective quadrant is always between 0 and 1, and pleasantly it's 0 when the two projective points are equal, and it's 1 when the two projective points are perpendicular. So now we come to the same key question that we started off discussing in the affine one-dimensional case. After we defined quadrants between 2 points, the next simplest situation was what happens if we have 3 points. In that case we had 3 different quadrants and there was some relationship between them, and figuring out that relationship was sort of the key starting point for a whole bunch of new developments. Exactly the same situation happens here. We've just defined the notion of projective quadrants between 2 of our projective 1 points. Okay, now what happens if we have 3 projective points? For example, A1, A2, A3. Then there are going to be 3 projective quadrants. Q1 says the quadrants between A2 and A3, Q2 the quadrants between A1 and A3, and Q3 the quadrants between A1 and A2. And so we ask, what is the relationship between these 3 numbers? For example, in this situation here, we have A1 is 2 to 1, A2 is 1 to 3, and A3 is -1 to 1. I'll let you check that the projective quadrants between these two is 1/2, between these two is 4/5, and between these two is 9/10. So we want to know what's the general relationship that's going to hold between these 3 numbers, no matter which lines we choose. So there is such a relationship, and it's a very important formula. In fact, it's one of the top 10 formulas in mathematics, in my opinion. And I'm not exaggerating here, I really do think it's one of the top 10 formulas in mathematics. And probably by the end of this series, you will probably agree with me. All right. You will see how this formula opens up all kinds of new areas and new developments in quite a variety of different things. It's really a remarkable and beautiful formula. Okay, so a major exercise for you now. Okay, at the end of this slide, please stop the video. Do not go to the next slide. You have now this fabulous project to do, to find this relation, to find the polynomial relation between Q1, Q2, and Q3. It's a great exercise even if you're a professional mathematician. It's quite a little bit more tricky or subtle than that one-dimensional affine situation was probably pretty easy. This one is a little bit more tricky, and it's very satisfying, and you end up with a beautiful relation. So you can own this relationship for yourself by discovering it. Okay, if you have done the exercise, let's see if your answer is the same as this one. Here it is, the projective triple quad formula. 3 projective 1 points, the 3 projective quadrances, and here is the relationship between them. Q1 plus Q2 plus Q3 squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared plus 4 times the product Q1 times Q2 times Q3. It's exactly the same as the triple quad formula, which is there, together with this additional cubic term. So it's no longer of degree 2 as it was in the affine case. It's degree 3 because that's a cubic. Okay, as an exercise, here's an alternate asymmetric form, which is Q1 plus Q2 minus Q3 squared equals 4Q1 times Q2 times 1 minus Q3. If we eliminated this factor here, then we would get the familiar asymmetric form of the triple quad formula. So this is not so much different from the affine story. Okay, we can generally expect this, that the projective story is somehow sort of following the affine one, but it's a little bit more complicated. It's a little bit richer. Maybe it's a little bit more interesting ultimately. All right, so those of you who have studied rational trigonometry, and good on you for doing that, you will recognize the formula. In rational trigonometry, the same formula occurs. It's a very important formula there. It's one of the main 5 formulas, and it's called the triple spread formula. And we'll talk more about that manifestation of it later on. That's really a sort of a 2-dimensional manifestation of the same formula. Here we're really interested in identifying it as a 1-dimensional phenomena, though, which is somehow more elementary in a way than this 2-dimensional appearance in regular rational trigonometry. It's useful when talking about the formula to introduce this function. We call it the triple spread function. That's denoted by capital S. So S of A, B, C is A plus B plus C squared minus 2A squared plus B squared plus C squared minus 4ABC. So what you get when you bring everything on one side of this triple quad formula in the projective setting. So that allows us, for example, to write efficiently that S of 4/5, 1/2, 9/10 equals 0. This is an efficient way of saying that these 3 numbers satisfy the projective triple quad formula. Okay, now here's a little bit of an exercise for you just to become a little bit more familiar with this particular form, maybe start to appreciate it. So the spread function on ABC is the same as Archimedes' function ABC minus the product for A times B times C. And here's another expression, just sort of writing it out a little bit differently. And here's another expression, which is quite different, well worth having a look at that. 4 times 1 minus A times 1 minus B times 1 minus C minus A plus B plus C minus 2 all squared. And one more as the negative of a 4 by 4 determinant. If you don't know what a 4 by 4 determinant is, don't worry. If you do happen to know what that is, then you can check that that's the same. It has a pleasant symmetric form here. ABC here, ABC here, and 1s, 1s with a 2 down in that corner. And this exercise is taken from my book, exercise 7.1. All right, so we're going to see this result play a major role. Clearly what we have to do is now explain why it's true. Okay, and that's a good thing for you to think about too. So between now and next lecture, why don't you think about how to prove this thing? Maybe you can prove it yourselves. And we'll also see that the Euclidean structure that we're imposing on the projective line by talking about this projective quadrants has an interesting ramification algebraically. There's actually an algebraic structure on this projective line, which is probably quite familiar to you once you see it written down. It's actually a very elementary kind of one-dimensional algebraic structure, which is still non-trivial and quite interesting. So lots more extensions from this. We're just entering this brave new projective world, and it's a very interesting world. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.